This is about panel data model. Um, so it is a very interesting example. Like the base model is like this. Okay, so we will think about the GDP for a country in a year. So the observation is over many countries like this and over many years. Right, that is the panel data. Right, so this year's GDP depends on the last year's GDP. That is the key part here. So we call this autoregressive or autoregression structure. So last year's GDP has kind of inertia. So for some reason, and but there is a coefficient rho zero, right? Like certain part of the GDP will disappear, like will be depreciated, but most of the part will be maintained. And on top of that, there is kind of the additional uh, contribution from other characteristics x, and there are two unobserved terms. Alpha is time invariant, country specific random shock that that stays over time. That's permanent shock, such as natural resources or some kind of cultural things, such as something like that. And epsilon is a transitory, idiosyncratic shock, so that is specific to just 1 year, right? Like financial crisis or things like that. So, and you may imagine any other cases, like for example, I may be a firm and the output may be sales, the sales, right? A firm sales may depend on the accumulated like reputation the firm has, or like your test score. Your test score may evolve over time, but there is some kind of consistency. So this autoregressive part will capture those kind of consistency. And usually the autoregressive part is between 0 and 1. If it's greater than or equals to 1 or greater than 1, then that causes a big problem econometrically. So we are not going to handle that. So you are going to learn that in time series. That is a huge research topic, separate topic. Um, and we are going to assume that we are going to assume really nice things such as X is all exogenous, right? X does not cause much trouble, and those two error terms, alpha and epsilon, are also uncorrelated, and epsilon are uncorrelated over time. So the previous year's random shock is uncorrelated with this year's random shock, and also for any past and the future. Okay. So okay, now let's think about the problem. Right? IT equals one more thing that I should have said here. Um, so when I say covariance or covariance, it is basically an expectation. But for example, when you think about sample mean of x, when you have panel data xit, then you can think about two different ways, or actually three different ways to take on average. You may take on average across individuals, right? Summation is through I, or you may take average over time, okay? Or you may take average over everything, right? So like all these three are okay, but in the panel data structure, like in so when I like in many cases, I'm going to be interested in this guy. So in this example, T is short and number of countries will or number of individuals, number of firms is large. It converges to infinity. So when I say expectation, I mean expectation across countries. And as you see, so in these covariances, I put conditions about T. That means the covariance takes care of I, but t must be like assumed what t I'm talking about. Anyhow, that's a digression. Back to the question, we are going to think about so I am going to write it this way, where UIT, the total error term, can be decomposed into permanent shock and transitory shock. Okay, in this case, we are particularly worried about the correlation between these two guys. And actually, X will be also correlated with alpha usually, right? So alpha may be included in like may affect xi because alpha is natural resources, cultural things, but particularly more important is yit, right? Because you can imagine something like this. Yit is just accumulation of all, like first I alpha I and epsilon it minus 1, epsilon it minus 2, epsilon I t minus 3, and all the past shocks are accumulated inside here, right? Because, like say, think about this, epsilon t minus 3 will determine yit minus 3, and this will affect yit minus 2 by multiplied by rho, and this will affect yit minus 1 using through the autoregressive structure. So it is affecting this. So in that way, all the past history of epsilon is accumulated inside yit minus 1, as well as alpha itself. Okay, that means if you think about all these guys and the contemporaneous random shock, epsilon t is uncorrelated with everything here. We assumed epsilon is uncorrelated with alpha. Epsilon is uncorrelated with all the past values. So epsilon is okay. But the problem is this alpha is correlated with this alpha. So alpha is entering in both cases, like in the regressor and in this error term. So alpha causes the endogeneity problem. That's the main problem we need to worry about. Okay, so also X may be correlated with alpha in many examples. So that is possible. There are possible correlations. Okay, let's think about B. Okay, the main problem is alpha. So we are going to take care of alpha by taking first difference. If you define delta yit as yit minus 1, so the difference, how much the GDP increased this year from last year, then you can say y0 yit minus 1 plus xit transpose beta 0 plus uit minus rho yit minus 2 plus xit minus 1 transpose beta 0 plus uit minus 1. Okay, this is just equations for yit and yit minus 1. And think about this. You can write this and this as rho 0 times delta yit minus 1. Simple. And this can be combined as delta xit transpose beta 0. And if you think about these and these, alpha does not change over time. It is alpha plus epsilon it. It is alpha I plus epsilon I t minus 1. So alpha will be cancelled out. So in the end, it only has epsilon it. Okay, so by the first difference, we removed alpha from the error term. So that is the purpose of doing this. Okay, now then let's think about the problem. So because alpha disappeared. First, x and epsilon are assumed to be uncorrelated with each other. So delta x is exogenous. That is pretty clear from the assumption, but this is the problem. Okay, so let me turn the page. So delta yi t minus 1 is yi t minus 1 minus yi t minus 2. And delta epsilon I t is epsilon I t minus epsilon I t minus 1. Okay, now I said y is the accumulation of the past random shocks. Okay, so then that means epsilon t is not in those guys. These guys are not including epsilon t at all. But the problem here is epsilon t minus 1 obviously is correlated with yt minus 1, right? Directly, it's contemporaneous shock. So if you think about expectation between yit minus 1 and delta yit minus 1 and delta yit, I would be worried about this guy, right? So even if everything else is nicely uncorrelated, still you have to think about this. So minus something like this. Yeah. So it is not, obviously it is not 0. So if you think about the first difference regression model, so this is the regression model. In here, we have two regressors, this and this, but it is okay. X is okay, but I just show that it is correlated with delta epsilon. So that is the major problem we are facing here, even if we delete x. Then, how can we do that? What is interesting here is the Arellano and Bond suggested just using yit minus 2 as an instrument. Okay, yit minus 2 first, look at this. It is uncorrelated with all these guys. So I said yit will include yit minus 2 depends on alpha and epsilon it minus 2, epsilon it minus 3, and all the past values. So it is uncorrelated with epsilon it and epsilon it minus 1. That means expectation of correlation between yit minus 2 and delta epsilon it is uncorrelated. Okay, so that's a simple observation, right? And then extending the same idea, you can also claim that yit minus 3, if available, will be uncorrelated with delta epsilon it. So delta epsilon it depends only on like epsilon it and epsilon it minus 1. So any value from the past is uncorrelated with those epsilons. Okay, so this is what Arellano and Bond suggested, and of course delta xit, or just without expectation, without difference, xit delta epsilon it is also valid IV. But so this is pretty obvious directly from the assumption, but let me restrict our attention to this relationship. Okay. Then let's think about part E. So I will think about very simple case where there are 4 time periods. You observe 4 years. Okay, and also I will ignore x. X does not exist. Okay, x will be ignored, and then we only have very simple single regressor example. this is a linear regression with this as an error term, and just this as an endogenous regressor. Okay, so then the moment conditions we can utilize here, because remember t is 4, so then what we can do here is the moment condition we can utilize here is delta epsilon I 4 is uncorrelated with yi2. Okay, and also delta epsilon I4 is uncorrelated with yi1, and also delta epsilon I3 is uncorrelated with yi1. So, like remember, we have to have at least 2 legs between epsilon and y, right? Delta epsilon and y should have at least 2 legs. So when t is 4, then this is all we have. Okay, that means right, like in the moment condition case, moment condition form, you write this as delta yi4 minus rho 0 delta yi3 equals to 0. Expectation yi1 is uncorrelated with yi4 minus rho delta yi3, and yi1 can be used as an IV4 3 times 3. Okay, so these are the 3 moment conditions we get. So it is interesting because these are the same thing and these are the same thing. It is some kind of like not one-to-one. So its notation is interesting. Like Arellano and Bond suggested notation like this. Say define Zi as a matrix. The matrix looks like this. Say yi2, yi1, and 0, 0, 0, yi1. So there are 3 moments. So they may write the moments this way. And then I'm going to define, say, delta epsilon. Of course, like what do you say? Say let's write it as following their notation. Vi is delta yi4 minus rho delta yi3, and delta yi3 minus rho delta yi2. If you then, our moment condition can be written as Zi Vi equals to 0. Okay, so it's 3 by 2 and it's 2 by 1. So it's total, like you get, let me put this as a function of rho. So it is a, so our moment function gi rho will be defined as Zi times Vi rho. So then you can handle kind of asymmetric form easily. Of course, if t is large, then it will be more complicated, because for example, for delta epsilon I large t, there are t minus 2 IVs. And for the previous period, you have t minus 1 instruments. And as you go for delta epsilon I3, you get 1 instrument. So it is kind of weird and interesting pattern. And as you see, as t goes to infinity, it will explode. The number of IVs will increase very quickly. So there are total t minus 2 times t minus 1 over 2 number of moment conditions. Okay, then everything else is pretty straightforward from now on. Omega is expectation gi rho 0 and gi rho 0 transpose. And it is, say, using our notation, zi times vi rho 0 times vi rho 0 transpose zi transpose. So there is nothing more you can simplify, right? So because zi is about yi and vi is about like delta y minus rho delta y, something like that. So everything is correlated and there is no simplification. Okay, just this is how you do it. However, still you may estimate the let's say think about weighting. How can you find a weight based on this omega? My idea is first have GMM, just minimize zi vi rho transpose zi vi rho. Okay, so this is one one preliminary estimator, consistent estimator, and then I'm going to estimate this omega as vi rho tilde in transpose zi transpose. So this will be a possible weighting metric. Its inverse. I'm going to use its inverse as weighting matrix. So then it will be an optimal weighting matrix. Okay. So then next, let's think about the derivative. The derivative is even simpler, right? It is, say, zi times this. So zi times minus delta y 4 and minus delta yi 3. Okay, I believe this should be right. Okay, and then it is just z is like bunch of yi, yy2, yi1, 0, 0, 0, yi1. So it is another matrix. So in the end, it does not depend on any parameter. So pretty simple. So therefore, g0 is expectation of the derivative, but derivative does not depend on any value, right? So minus delta yi4, minus delta yi3. So its expectation is g. So this is easy. And then let's think about the asymptotic variance. Asymptotic variance will follow G transpose omega inverse G0 and their inverse. Okay, and then just go ahead and plug this into this. Like we calculated G0, we calculated omega. So we know them. There is no more algebra you need to do because there is no simplification. I just did it to explain how to calculate the variance. How to calculate the variance? First, G is easy to calculate. G hat will be just sample average zi and minus delta yi4 minus delta yi3. So this is your G hat. And omega hat will be also similar. It is like this, like same thing, but we are going to use the final row. transpose CI transpose. This will be your omega estimator. So plug them in to obtain the final variance estimator. The variance will be easily estimated.